Saxon Advanced Mathematics, Lesson 93. Grab your trig data page, ladies, because we are going to be using this today to work on some identities. Again, we are not going to be using sum and difference identities. We're going to be using Pythagoreans, and we're going to be using reciprocals, and we're going to be using what we call our quotient functions as well, especially this one. So you won't need the sum and difference ones, which I have on a different page, so that's why I'm thinking grab one but not the other. But in any case, keep this at the ready because we're going to need it in just a minute. All right, I want to show you. We're on the last week of lessons. Yay! We're getting so close to the end, you guys. And I'm really going to be excited to give you your break because you've worked very hard. Okay, these advanced... Oh, and there's another part to this. Don't worry, the second part is very straightforward. Trig identities, again, we're given what looks like an equation, but we're asked to reshape the left side to make it look like the right side. We did some of these a few weeks ago, and then we sort of took a break and we did all the crazy business with the sum and difference and the half angles and the double angles. That's like its own little corner of crazy. Now we're going back to the identities, but we're going to use some new tricks to help us reshape the left side to make it look like the right side. And I think it was Laura that asked me, like, how do you know, excuse me, how do you know what to do? How do you know where to attack them and dig in? And how do you know which identities to use? And I'm going to speak to that a little bit more today because that is tricky. That is a hard, that's the whole trick of these, is figuring out what are you supposed to be doing here. All right, so let's just dive in with example 93.1. And it says, show okay, I'll give you a second to finish copying. So let me just remind you that having B's here is fine. That doesn't mean anything. We can have a theta, we can have an X, and lately we've been doing this whole A and B thing. It doesn't matter. What matters to us is that they're all the same, and that is really great. We love that. Now, how in the world could we possibly make this look like this, right? It seems kind of impossible. So here's a hint. When you're trying to figure out what to do, look at the denominator. Denominators, okay? And think about how can you get the one on this side to look like that, the one on that side. And when I look at this, I go, well, it's almost like the Pythagorean theorem, right? Cosine squared equals 1 minus sine squared, except this is not squared. This side is squared, but this side is not squared. So my idea is, what if we multiplied top and bottom by cosine of b so that we could get the square and then we could substitute this in? We wouldn't be all the way there because this side's not squared, but it's a starting place. It just gives me an idea of something to do. So what I'm going to do is I'm going to multiply. Again, this is what we're trying to make it match, so I can ignore that. I'm going to multiply top and bottom by, I'm going to write it over. I don't want to squish it. I'm going to multiply top and bottom by cosine of b. And again, the reason that I want to do it is I want to get the squared here, and then I want to substitute and see if that helps me at all. All right? So on the top, I'm not going to try and multiply it. I'm just going to leave it cosine of b times 1 plus sine of b. I'm not going to do anything with that. I don't even know what to do. And then down here, I'm going to write cosine squared b, But then that is equal to, I'm using this line right here, right? 1 minus sine squared b. Right? So this is what I originally had, but I'm going to squiggle that out because I've now substituted using my Pythagorean identities. I substitute that in. Right there. Okay, and we are allowed to do that. We can multiply top and bottom just like any other kind of algebra. We put that in there. We could distribute it, but I don't want to do that because I'm not sure that's going to be helpful. I'm trying to get the denominator straightened out. Now, this, I recognize another pattern. So we're always looking for factorable patterns. And this is where previous year's work becomes so important. This is a difference of 2 squares, right? 1 is a perfect square, sine squared b is a perfect square, and we're subtracting them. How do we factor a difference of 2 squares? Oh yeah, it's a minus b quantity, a plus b. And you may have memorized that in the opposite order with the plus first and the minus second. It doesn't matter. Either way, I write it both ways. So now we're going to, again, we're still just working on the denominator. I really don't have a goal in mind. I'm just trying to do anything I can that I think might kind of break this down. It's kind of like, I hope this metaphor makes sense to you guys. Do you ever untie knots? I love untying knots. I've untied knots. My dog has a really, really long 50-foot leash that she often gets knots in. I mean, I do because I coil it all up and then I put it back out again and it has knots in it. I have some blinds on my windows, you know, like bamboo blinds that have the long cords that you pull and they get knots in them sometimes. I love going fishing and untangling lines and fishing lines. This is kind of like that. When you're untangling a knot, you don't know exactly what you're trying to do when you first start. You're just trying to loosen up the knot so that you can see the way the cord is winding around, and maybe you'll find something that will help you make a big jump. That's what we're doing here. We're just trying to loosen this up and get it so we can see a little better what's going on. So now I recognize that this is a perfect square, 2 squares, difference of 2 perfect squares. I'm going to factor it like this. Top stays the same. And then I'm going to use this pattern to rewrite this. So it's going to be 1 minus the sine of b, not squared anymore, right? Because we break it down. And 1 plus the sine of b. Oh, now I'm excited. Now I'm excited because look, those two will cancel. They have addition in them, but they're only being multiplied as quantities, so we're allowed to cancel them. So that cancels and that cancels, and look what I have right here. There it is. We did it. Yay. I did not have a specific plan in mind. I did not know, oh, if I do this, then XYZ will result and I'll have my answer. I did not know that. I was just loosening it up, paying attention to the denominator, and trying to do anything that might get it closer, okay? That's the secret, is don't worry about having a grand plan at the beginning. You might not see it yet. Just loosen it up and do what you can and look for patterns. The next one. I kind of want to start on a fresh page because this one is going to be kind of long. I have a feeling. Example 93.2. Ready? John's kind of into the bees this time. All right. We have to make that look like that. Lord have mercy. Okay, I'm going to circle this because I remember I don't want to change this. I just want to get to the same target, right? I remember that secant equals 1 over cosine, and cosecant equals 1 over sine, okay? And then I'm also going to remember that tangent equals sine over cosine, right? Okay, now, one of the rules that we also talked about in the past was turn everything on the left-hand side into sine or cosine. Simplifying it makes it a little bit easier to reshape it, okay? And I think last time we had that, right? We had it in sine and cosine. That makes it easier. Happily, we were trying to shoot at a target that was sine and cosine. This time, our answer, our right side, our goal, is a little more complicated, but still, I really like to switch the left side to sine and cosine, then reshape it and see if we can get it to this. This helps me because it reminds me of what these actually represent, okay? So what we're going to do is we're going to change these tangents into sine and cosine. Okay, so that's what I did. I just changed it into sine and cosine. Now, I'm going to go to the denominator again first. I need this to be, now what I would like to do is I like to get my head on straight. So this, if I what I want this to look like is 1 over the cosine of b minus 1 over the sine of b, right? That is what this is. So I don't necessarily want to reshape this, but I want to understand what I'm trying to get over here. Gracie needs to go out. Hang on just a second. Okay, good job. Good. Okay, I'm back. Here, sorry, I just leave you for moments at a time. Here is the thing about Grace. She drinks water like a Tasmanian she-devil. It is so messy, and she splashes water all over, and then she has water like cascading down her lips and dripping onto her ample chest hair. It's just a disaster. We call her the Swamp Queen because she's just like a wetland by the time she's done, which is especially ironic because our previous dog, his name was Ranger, who looked very much like Grace, was a dapper gentleman who never had a crumb of food on his lips or a single drop of water. He just was dainty and proper, and she's this wild woman. So she does not get to have water in the house. She has to go outside to drink, which is fine, but that just means I get interrupted like this. So thank you for being patient with Grace. Okay, what I was saying before I was interrupted was that I just want to remember what this looks like in cosine and sine so that I know when I get there, because secant and cosecant don't fit as neatly and quickly into my head as sine and cosine do. So I'm trying to make this look like this, and I go, hey, wait a minute. This looks good, right? This cosine B, this is what I've got on the bottom. That's what I want. And again, I'm paying attention to the denominator first, and I'm hoping that the numerator will just fall into place. So I'm comparing this expression down here to this, and I'm saying, I've got this. If I multiply both sides of this by, I can think of it like this, 1 over sine B, and I would have to distribute it, right? Then that would give me 1 over cosine B here minus 1 over sine B there. It would work, wouldn't it? This would be perfect. Now, I have to do it to the top too, and I'm not sure if that's going to work out as well, but I'm going to fix this denominator and make it look like that, and then we'll figure out what we've got. So I'm going to multiply. Just a second. I'm writing pay attention to denominator, because that, loosen up your knot, right? Loosen up your fishing knots. Okay, so now I'm going to multiply first on the bottom. And it's a distribution, so I have to do it to both parts, right? When I multiply here, the signs will cancel, and I will get 1 over the cosine of B minus, and then 1 times this is the sine. I hit my target. That's what I want. Now, I don't know if the numerator is going to work out. I might have to do something more up there, but let's see. When we multiply the top, and we have to do top and bottom, right? This also cancels, and I get 1 over cosine of B plus 1 over sine of B when I multiply it by 1. And look, that's exactly what the top is. So I can rewrite this. 1 over cosine of B is secant of B plus, and this is cosecant, whoops, of B over 1 over cosine of B is secant of B minus cosecant of B. That is exactly what I was going for. I hit my target. Yay. Remember, this isn't me trying to actually change this. This is me just trying to see it in terms of cosine and sine. All right. I still want to hit this target, but this just helps me understand my target a little bit better. All right. So all the things in Puffy Clouds of Knowledge are my tips and hints to you as to how to start to think about what you can do to fix these. Again, pay attention to the denominator. Don't worry about the numerator. Just let that go along for the ride and see what happens. All right, we have one more of these. 93.3. Show. Okay, this one gets a little crazy. Kind of drives me crazy, this one. X times the sine of theta. Let that freak you out for just a minute. Couldn't fit it all on one line. This is the whole left side. This is the right side. We have to make this look like that. Huh. All right. Well, we can see that we're told to square. Oh, this should have a square on it too. Sorry. We're told to square these. And if you think of it, this is just like x plus y quantity squared plus x minus y quantity squared, right? That's a simpler way to see this. So imagine a simpler form is another good hint that I can give you, right? Drop the trig functions out of it and just look at the other parts of it. What would we do if we were trying to simplify this, right? Well, we would have to square the two binomials, and then we would add all the, we would put all of those long expressions together, and we would hope that a bunch of stuff would cancel out, right? So that's what we have to do, is we have to square these, we have to actually square these binomials in their trig form. Now, the process of doing that is exactly like if we were doing this, we just have more to write each time. So let me show you what that looks like. So the first step in this one is we're going to square the binomials. Here's the first one. It's x sine of theta plus y cosine of theta times itself. Right now you're just thinking, what in the world? But it's not that bad, okay? Now you know my story about the dance, the kids in the 1930s in their Saturday morning dance class, and they're wearing their little scuffy brown Oxfords, and the girls have on little dresses, and the boys have on, I don't know, what do they have on? I think their hair is like wet combed. You know how moms used to do that to their little boys to try and make it lie down? I think they're wearing like little short-sleeved plaid dress shirts that are buttoned up to the neck, and their little dungarees. And they're dancing, right? The teacher's making them dance with each other. And here are all the boys sitting on their side. Here are the girls on their side. The sun's streaming through. We can see the little dust motes sparkling in the air. For some reason, I always need to see that when I'm imagining this. And we're going to have this girl dance with each of the boys, and then this girl will dance with each of the boys. That's how we square binomials. I know. It's perfectly natural, right? This is the way every math teacher teaches it. All right, when we multiply this by this, we square the x's and we square the trig function. This times this equals this. Oh, okay. Now, what about when we multiply this girl times this boy? Okay, it's plus, we see that, and we put together the coefficients. Whoops. And then we list them, right? Because they're different. I always put sine and cosine in this order. Sine comes first. All right, thank you, young lady. Sit down. Now it's her turn. She multiplies with this. Well, look, it's the same thing. It's xy, sine of theta, cosine of theta. And now she dances with him. Plus y squared, cosine squared theta. Now we add all this up. This becomes 2xy sine of theta cosine of theta plus that's squaring the first binomial, okay? So we've squared this, and this monster is what we get. Now, what I'm going to do is I'm going to square the second binomial down here, and then I'm going to leave room to write the answer there, and then we'll do our combining of like terms. So now I square the second binomial, x cosine theta minus y sine of theta. That times itself, right? Okay, we're following this same pattern. All right. Here we go, dancing time again. X squared cosine squared theta minus, again, we put the letters together and then the trig functions in the order that we're used to seeing them. Thank you, miss. This girl's turn. Another minus. Beautiful. And now here, look, we're going to get plus. We're multiplying y squared sine squared theta. Okay, when we add them together, I'm going to write the answer up here. It's x squared minus 2xy plus y squared. Okay, so there's our, this was our first binomial, this was our second binomial, this is the multiplied form of the first one, this is the multiplied form of the second one. Makes sense? And we're adding all of this outrageousness together. So, what cancels? Look, this whole middle business drops out, right? This all cancels. Right? And then we're going to have, I'll write it here. We're going to have x squared sine squared theta plus x squared cosine squared theta plus y squared. I'm going to do the sine first. Okay, so we just have the middle terms cancel and we just have the beginning two and the ending two. All right, I feel good about that. Now, again, what do we do with this? We don't have any denominators in this one, so we're just looking at the whole mess. What I see is a factoring pattern here. I see x squareds in front of sine plus cosine, and I see y squareds in front of sine plus cosine. Right? So I'm going to rewrite this down here where I have a little more room. I'm going to take the x squared and I'm going to factor out sine squared theta plus cosine squared theta. Do you see how I did that? Those are the two terms I'm factoring. I pull out the x squared from both of them and I'm left with sine squared theta plus cosine squared theta. There it is. Now I'm going to do the same thing over here. I'm factoring these two together. I'm pulling out the y squared from both of them. It's positive, so that's why I put the plus there. And then this becomes sine squared theta plus cosine squared theta. Now, hopefully, there's a little bit of a bell going off in your head. Going, that looks familiar. Sine squared theta plus cosine squared theta. That sounds like a Pythagorean identity. And look at that. It's equal to 1. So guess what? We're going to change those into 1s. Well, this I shouldn't put a circle around it because it confuses it with this. Both of those turn into 1, so all of that gibberish goes away, and we just have x squared times 1, so I can ignore it, plus y squared times 1, so I can ignore it. Oh, I'm supposed to circle this. And look. Oh! The gates of heaven have opened, and the holy light is shining out upon us. You guys, we did it. That was really intense. This one was an exercise in learning how to square binomials that have trig functions in them. And you learned it's not all that hard. It's kind of intuitive, right? And then we just added all the like terms and we smushed it. And then at the very last minute, we realized that we had an identity that we could use. But all of this work did not involve the identities really at all, did it? Yay! That's example 93.3. Okay? That's our work on advanced trig identities. Will these be on the test? Heck yes, you better believe it. Like I said, for the test, I will give you a worksheet to fill in. I will not tell you the exact, I will not give you the identities, but I will set this up so that it's easy for you to fill in all the information. It'll be sort of pre-organized for you. And then you'll be able to use that on these problems. But there will be a problem like this on the test. Yes. Okay. Ready? Now for the easy part. This is called triangle inequalities, I guess is what John calls it. That doesn't really sit right with me, but it's okay. First, I'm going to tell you something that you already know. If we have a right triangle and we call the legs A and B and we call the hypotenuse C, there's a relationship. A squared plus B squared equals C squared. Yay! It's called the Pythagorean theorem, right? We know that. That's cool. Now, here are two other little facts. Let's say it's not a right triangle. Let's say that it is an obtuse, right? And so we still want to call this longer side C, but we'll call these A and B. In this case, I just want to rewrite this. C squared equals A squared plus B squared. Okay, I want to write it in this form. In this example, C squared is actually going to be greater than A squared plus B squared, which kind of makes sense because we can see, well, it's not a right triangle, but this thing is stretched really long, right? It's kind of disproportionate. And so we can see, okay, that seems fairly logical. And then conversely, if you squish that long side in, right, like that, and make them all more or less the same size, then the C squared is going to be less than the total of the A squared plus the B squared. This is somewhat intuitive, but we call these triangle inequalities useful because we can use them to predict what the relationship will be, whether it will be, remember, this is an acute triangle, this is an obtuse triangle, and this little darling is a right triangle. We can use these inequalities to help us predict whether we're dealing with an acute, obtuse, or right triangle. No, I'm not going to say anything more about that. Okay, so here is the way, there's two examples here. 93.4. Is the triangle whose sides are 3, 4, and 5, is it a right triangle, an acute triangle, or an obtuse triangle? Okay, all we have to do is set it up. We always let the longer side equal C. So what we want to do is we want to set it up as C squared something A squared plus B squared. Okay, so we're going to define the numbers, and then we're going to see what's true. Equals, greater than, or less than, and then that will tell us what kind of triangle we have. All right, so we're going to let this be 5 squared. Mystery symbol. Here are my numbers. 3 squared plus 4 squared, right? We always let the longer side equal C, even if it's not clear what's the hypotenuse. All right, 25. 9 plus 16. 9 plus 16 equals 25. Aha! So in this case, the two amounts are equal, so that tells us we have a right triangle. Yay, that's the correct answer. Make sense? And then we have example 93.5. And it says classify the triangle whose sides are 4, 7, and 5. Once again, John's just asking us those categories, and we use these tools to help us figure it out. We let the longer side equal the C, so we've got 49 something to 4 squared is 16, 5 squared is 25. That equals 41. Okay, 49 is greater than 41, right? And so this must be obtuse. And it is. Makes sense? That's kind of easy and kind of fun. Remembering that obtuse triangles are the greater than and acute are the lesser than. You can memorize it, but you can kind of visualize it, right? In this one, the C gets stretched bigger, and in this one, the C gets smushed smaller. That's how my brain sees it. Will there be one of these on the test? Maybe. I consider this a really easy problem. So if I feel like we need an easy problem, which we probably will, because it's going to be a hard test, right? It's going to be a lot of crazy big problems. And like I said, I will give you a place to write down all your identities ahead of time, and I will give you a blank unit circle so you can fill that in and use it. And you will be able to use your calculator on certain problems, so you can start thinking about that too, making sure you have access to all of these tools. All right, that's the end of lesson 93. Thank you for staying with me through a long lesson. Thank you for being patient while Gracie got her drink of water. And I will see you tomorrow for lesson 94. Goodbye.